Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 62, and this problem asks us to explain why the carbon-carbon alkene double bond of an enol, so let's draw an enol, so remember an enol is an alkene that's directly bounded to an alcohol. So why is this alkene double-double bond of an enol more nucleophilic than just an alkene double-double bond without any enolic alcohol, despite the fact that this oxygen atom is electron negative, so it inductively withdraws electron density from this alkene double bond. So therefore, you would assume that this would make it more or less actually nucleophilic than just an alkene. But remember, enols exist in some sort of tautomer with the more stable keto form. So we know that even though there is a polarization with electron density being pulled towards this alcohol, giving this carbon here a delta positive sign, even though it's withdrawing electron density away from this pi bond of the alkene, we know that the driving force that actually makes this alkene such a strong nucleophile is the fact that oxygen, using one of its lone pair electrons, will come down, making a new bond. When you make a new bond here, so it makes a new pi bond here, then this carbon here would get 5 bonds, but carbon cannot get 5 bonds. So one of these bonds must break. And which bond will break? Well, the weakest bond will break. And we know that because of the pi orbitals being on the sides of the sigma orbitals, pi orbitals are weaker than sigma bonds. So we know that the pi bond will break first. So now these two electrons that make the pi bond are going to break. They're going to go through this carbon nucleus and do nucleophilic attack. So the driving force that makes the alkene of enol so much more nucleophilic than just any regular alkene is the fact that you get a tautomerization to the keto form that forces actually this pi bond, these two electrons that make the pi bond, to break and act as a nucleophile. So this is the driving force. The keto tautomerization is the driving force that makes this such a better nucleophile than just any alkene, which, for this to break and to act as a nucleophile, now you're going to go make a carbocation with some sort of substituent you added here, so any R group. So why would nature want to go from neutral compound to something that's charged? There has to be a good reason for that to happen, such as the input of energy or formation of a more stable product. So obviously, this is not as likely to occur from going to neutral to something charged as is the keto tautomerization. Keto tautomerization is much more favorable because a carbonyl pi bond is far more stable than just an alcohol with this enol form, essentially. So this is why the keto form is far more superior and is far more abundant than this enol form because of the stability of this carbonyl bond, which makes, as a consequence of this happening, makes this alkene far more nucleophilic than just any order alkene that is not enolic in nature.